you've already seen. I just want to do a quick review of what we did. And it's going to be sort of quick. I hope it's going to be quick. I don't want to spend the whole time on this, that's for sure. We talked about what is survival analysis, and we did it through an example. Whoop, where is it? We talked about it through this example, looking at trying to compare two groups in terms of their survival times. In this case, it was times while they were in remission. And we noticed that that you can talk about how long they survive. You could measure the thing you might want to measure to compare the two groups is something called a hazard rate, an average hazard. And if you want to compare the two groups, you typically take comparison of the hazards, and so one hazard divided by another is called the hazard ratio, and that's the main measure of effect that we're going to be dealing with when we talk about survival analysis. When you do any kind of a survival analysis, you're essentially going to get a hazard ratio, and what you want to do is you want to look at the value of the hazard ratio, see how large it is, see whether that means that one group is doing better or worse than the other. And then you want to get test a hypothesis about whether that hazard ratio is significant or not, significantly different from the null value of 1. And then you also want to get a confidence interval around that. And that's the case whether you're just doing a simple, simplistic analysis comparing two groups without any other covariates, or whether you have covariates, and you're even going so far as to do some kind of modeling using any one of the modeling procedures that are available. We're going to focus on the Cox proportional hazards model. And we talked about, so that's what survival analysis is all about. It's trying to look at time until failure, and there's an event of interest that's typically, it could be a good event, it could be a bad event. We often say when the event happens, somebody's failed, even though it could be good. We talked about censoring, and that the censoring essentially means that you don't necessarily, for some people, you don't know whether or not they got the event. All you've done is followed them for a certain amount of time. You know whether they dropped out of the study, whether they were lost to follow-up, or whether they survived until the end of the study, but you don't know what happened to them. You don't know whether they got the event or not, and that's censored data. And when you have that, that's a problem because you don't have all the information you want to have about some of your individuals. And we talked about right censoring and left censoring, and most of the kind of censoring we're going to be dealing with, or for as far as we're concerned for this course, is going to be right censoring, where the true time at which somebody survived is longer than the time you've observed. That's called right censoring. Remember that? We talked about that last time. We looked at the basic data layout. I'm just sort of skipping around here. We talked about the notation for survival analysis, where capital T denotes this variable survival time, and little t denotes a specific value you might be interested in, to seeing whether somebody's survival time exceeded some specific time of interest, whether capital P, whether the probability of surviving is greater than, say, 5 years. And then we have to worry about not only the survival time when we're talking about survival analysis, we have to also try to determine whether somebody failed or was censored. We need that information too. And that's a variable that's going to vary from subject to subject. And I'm calling that variable, the notation I'm using is D in the text. So if you're doing a survival analysis, you have to know, in your data set, you have to have a person's survival time, and you have to know whether they failed or were censored. And then we introduced two terms. One is the survivor curve, which is essentially, or the survivor function, which is a function that starts at 1 at time 0 and eventually winds its way down towards 0 as time marches on, so to speak. And survival function probability capital T is greater than some specific value of T. If T is 0, the survivor curve is 1. And we also talked about the hazard function. The hazard function is a way of looking at survival sort of from the opposite end of the coin, in the sense that you're looking at whether somebody has failed, and the hazard function is the instantaneous potential for somebody failing at a certain point in time. That's what this expression means. If you ignore the limit part of it, it means the probability that somebody fails within a small time interval, given that they survive up to the beginning of the time interval. When you divide by delta t, it's per unit time. So we're not talking about this h of t is not a probability. Once you divide by delta t, you're talking about a rate. And so a hazard function is some number between 0 and there's no necessarily upper bound to what it could be, but you're talking about a rate. I also mentioned that you can get one survivor function, you can get the hazard function from the survivor function mathematically, you can get one from the other. As I said, if you know one, you can get the other. And that means that regardless of how you specify the way you're doing your analysis, if you say, I'm going to do this analysis, I'm going to specify a hazard model for my study, you can get a survivor function that corresponds to that hazard function for your data. How are you going to do that? Well, you're going to use a computer program to do that. And the computer program you're going to learn how to use is PH-REG, which stands for Proportional Hazards Regression. That's the program you're going to learn how to run survival analyses, how to run a Cox model, how to state the model when you're running the program in terms of a hazard function or hazard model, and what you wind up having to do to get your fitted hazard model, or when you actually analyze the hazard model, and then when you want to get a survivor function, what you have to do in the computer, with the computer, to get a survivor curve. How do you plot the survivor curve? So you'll be learning how to use PH-REG to plot survivor curves. And when you get this take-home final at the end of the course, you'll be getting a bunch of data where you're going to be asked to run a bunch of survival analysis, answer a bunch of survival analysis questions, some of which is going to say, well, analyze this and plot the survivor curve. You're going to have to plot some survivor curves, so you're going to have to learn how to do that. And so anyhow, so we talked about that. We mentioned that in theory, the survival curve is sort of like a smooth curve, starts at 1, goes down towards 0, but in practice it's usually plotted as a step function, where you consider the steps change at different points at which people fail. That's when you go to a new step, essentially. That's what that means. You'll see that. And again, the relationship between a survivor function and a hazard function, so there's a mathematical relationship. You're never going to have to work through that because you have a program that's going to do it for you. Then we talked about the basic data layout for the computer. The basic data layout basically is you have a line of data for each person in your study. So you have n people in your study, you have a line of data for each person, and in that, for a given person, you have their survival time, whatever that is, whether they failed or were censored, and then you determine their failure status, whether they were censored or failed, and then you have the explanatory variables, the variables you want to consider in evaluating some relationship between maybe an exposure and an outcome, maybe controlling for other variables. That's the data layout for the computer. And then I also talked about a data layout for the theory, for understanding what a survival analysis is. We'll look at this a little bit more today in today's class, but basically what this requires you to do is rather than just listing subjects one under the other, you actually have to sort of consider when people failed, and you have to sort of consider the ordered failure times. And you set up a table where T sub 1 in the parentheses, T parentheses 1, is the earliest time at which somebody fails, and T2 is the next earlier time at which somebody fails. And in order to set things up, and we'll talk about this again more today, in order to sort of set it up so you can actually get an appropriate plot of a survival curve, you usually have to put in a T of 0, which is basically the start time, and you usually have to have this thing in that table also. Then you have a column which describes the number of failures at each time that somebody failed. it's possible that 3 people could fail at time 6, as it was in that remission time example. So M1 would be 3 if 3 people failed at time 6, and M2 might be 1 if 1 person failed at the next time. So that's the second column, and the third column describes the number of people who were censored between one failure time and the next failure time, the next ordered failure time. If you add up the total number of censored and the total number of failures in these 2 columns, you get everybody in your study that you're dealing with. And then the last column describes the risk set, and the risk set describes the subjects that are at risk in any particular time where somebody failed, or even any particular time at the start of the study. At the start of the study, everybody's in the risk set. At the time of the first failure, also everybody is in the risk set just prior, like 1 microsecond before somebody failed. So everybody's in the risk set just prior to the first time at which somebody failed. Like in the example, in the remission time example, everybody, even though the first time that people failed in this group was time 6, there were 21 people in the risk set just prior to time 6. That's what we're saying. Okay, and then the next time which somebody failed in group 1 was time 7. So how many people are in the risk set at the second time somebody failed? Well, you lost 3 here, and also remember the pluses we talked about. 1 person was censored between time 6 and time 7. So how many people were lost? Or how many people do you get rid of? Basically, you get rid of 4 people. So the people in the risk set, the risk set at time 7, when at the second failure, has how many people in it? 17. You start off with 21, it has 17. 4 people have gone. Okay, so now the reason why the risk set idea is important is because, and we're going to see this, is that, see, what happens is the risk set, and particularly the number of the people in the risk set, goes down, right? As you start off with everybody, and then it drops as people either fail or get censored. And when you're trying to eventually do even something simple, plotting a survivor curve, what you want to do is you want to say, well, okay, as people drop out, I'm not going to count them in coming up with my estimate of what the survivor curve looks like as we keep moving along over time. So I'm going to consider the people that are at risk when I'm going forward in time, and I'm going to not consider the people that are at risk, they're already gone. So the risk set's changing, and as the risk set changes, and I want to find the probability of surviving at some particular time later on after the start of the study, what I'm going to do is consider those people that are still left to evaluate what that survival probability is. Just sort of saying it without going into the details here. So we did this, and then one of the things we did was we looked at an extended example where we added a variable to the data set, and the variable was log white blood cell count, because if you're talking about remission leukemia, one of the predictors, one of the prognostic indicators of survival if you have leukemia is how big is your log white blood cell count. So that's a variable you might want to control for. So in this case, we had 21 people in each of 2 groups, but we also have their white blood cell count, and the variable of interest that the investigators thought was a better predictor than just white blood cell count by itself was log white blood cell count. And so we want to control for that. 2 ways to control for a variable. The simplest way, as you learned, is to stratify on the data. Stratify on the variable you want to control for, right? That you learned about stratified analysis. So if your variable is log white blood cell count, and as you can see, it's a continuous variable, and you want to stratify on it, what you're going to have to do is somehow decide on categories of this variable, log white blood cell count, and then break up the data into strata of categories of log white blood cell count. And what you might then want to do is come up with a comparison of group 1 and group 2 within each of the strata. So you get several hazard ratios over different strata. That's a stratified analysis. Now, if it turns out you have more than one variable, or even if you have one variable, but you could have several variables you want to control for, then the other way to do that is to use a mathematical model, just like we did when we were doing logistic regression. But now the mathematical model is a different model. It's going to the first guess at the model is going to be a Cox proportional hazard model, and it's going to have a bunch of predictors in there, and the outcome variable is going to be survival time, although you have to also know whether a person was failed or was censored in order to come up with a way of fitting the model. So the last thing I did was I said, well, suppose we take this data, which now has 21 people in each of two groups, and we say, let's analyze this data set to compare the two groups, the people who were treated versus the placebo people, adjusted for controlling for log white blood cell count, and see if there's a treatment effect, see if there's an effect on survival time of being in one group versus the other. Well, in that case, we have to put the data together for the two groups. So instead of just looking at the groups separately, we put all the groups together. We have a data set with 42 people. And some of the people are exposed, some people are unexposed. There's the ones, and the ones here are exposed, and there are the zeros, are the ones that are unexposed. We have their log white blood cell count. We also have their time, survival time, and we also have whether they were failed or censored. And you notice all the people in group 2 have a 1 because all the people in group 2 failed. So that's the value of that variable D, the failure time, the failure status variable. And then I showed you at the very end of the class, I showed you this output. I showed you the output for 3 models. And my message here was that even though I didn't show you the formula for the model, for each of those models, basically I said you work with these models the same way you would work with a logistic regression model. I mean, it turns out whatever the model looks like, the way you're going to fit the model or estimate the parameters in the model, whatever they look like, you're going to estimate that using what's called maximum likelihood estimation. So if you want to get a test of hypothesis, when you're using maximum likelihood estimation, you learn that there's a wall test and there's a likelihood ratio test. So that's the way you do tests. You want to get confidence intervals for when you're doing a Cox model, as just similar to the way you do for a logistic regression. There are these large sample confidence intervals that in the form of e to something, an estimate plus or minus 1.96 times the standard error, and you exponentiate it. It's the same kind of formula. I didn't show you the formula, but I showed you at least the outcome. And the formula for the hazard ratio, when you're fitting any one of these models, is an e to the beta formula. So in Model 2, for example, when we looked at that, Model 2 doesn't have the product term. The product term was in Model 3, and when we looked at Model 3, we found that we looked at and we could decide that you didn't need the product term. It wasn't significant, so we didn't need that. So Model 2, it would be maybe our next choice. And if we were looking at a no interaction model, and if we wanted to look at, even if we didn't know what the formula for the Cox model looked like, it turns out that the estimate of the hazard ratio from this output is e to the beta, where beta in this case is the treatment variable, is the coefficient of the treatment variable, and it's 1.29 raised to exponentiated is 3.648. By the way, I did change the way I presented this data a little differently, because if you may recall, you may not recall, when I described e to the beta in the previously, this was called risk ratio, but the way the updated output looks, it says hazard ratio. It's still e to the beta, that's how it's computed. So I just try to, represent this in the form that the computer actually shows it to you. And it also gives you the confidence intervals around the 3.648. Now, let me just ask you this. If there's Model 2 and there's Model 1, which model do you want to use? Model 2 or Model 1? How do you decide that? Well, what do you want to answer? Do we need a control for log white blood cell count? Isn't that what we did when we were doing logistic regression? Do we need a control for log white blood cell? How do we do that? How do we decide that? Is log white blood cell count a confounder, right? So what do? Is we say, well, the measure of effect here is hazard ratio. It's not an odds ratio. The measure of effect is 3.648. If we control for log white blood cell count and it's 4.523, if we ignore it, is that a meaningful difference? Remember, is that more than 10% difference? That's what we did to assess confounding, right? It's no different when we're doing survival analysis. It's the same idea of coming up with the best model. And if you decide, and it turns out it is a 10% difference, 10% of 3.648 is 0.36. You add and subtract, you get something that's more than 10. 4.5 is more than 10%. So you wind up saying that of the two models, the one I'm going to use is model 2 because I need a control for log white blood cell count because it's a confounder. Regardless of precision, I need a control for it's a confounder. If I didn't need a control for it, I then might evaluate precision, just like we talked about earlier in the semester. You with me on this? This should be fairly. Now, the other thing I wanted to tell you was, you see model 1 only has treatment in it. That's the only variable in there, okay? What are we essentially doing with model 1? You notice that the hazard ratio is 4.523. E to the beta is e to the 1.509 is 4.523. Well, if you actually go back to the original data set where we weren't controlling for anything, you remember what the hazard ratio was comparing the two groups? It was 4.6. This is just round-off error. But essentially, when you fit a Cox proportional hazards model, which we haven't shown, we'll see that next time. When we fit a Cox proportional, and there's only one variable in it, and it's your exposure variable, and it's a 0-1 variable, you're essentially doing the same thing as doing a crude analysis without fitting a model. You're just comparing two groups and getting the hazard for one divided by the hazard for the other, and you can do it using a model, but you don't need to do it. The reason why we do the models is because we have other variables we want to control for. Okay, so you're with me on this, I hope. Okay, so now we're ready to move on, I hope, unless you have very specific questions you want to ask. So now the next thing I want to talk about is, well, how do you plot survival curves? And so that's what we're going to do. There's a bunch of other things I could try to squeeze in here, but I want to make sure I talk about this before I try to squeeze anything else in there. Okay, so Kaplan-Meier and the LogRank test. And as I think when I asked you on Tuesday about this, most of you have had some kind of introduction to this, or you know what the Kaplan-Meier curve is. Do you know it? You know how it's, I mean, one thing is to know what it is, what it means, or how you compute it, how it's done, or what the formula is for how it's done. And the other thing is, well, how to get the computer to do it. That's the main thing you want to know. How does the computer do it? But you also want to know what it does or how you put it together. So we want to talk a little bit about that. And so I'm going to say a little bit about that. I'm going to skip a few things that are at the very beginning because of time. The very beginning, I have some examples, but I'm going to skip this, which is some simple things that about how you would come up with a survival curve. But I want to skip it because of time. So, you might say, well, maybe this could be talked about in the lab. But this is, I think I want to go on to skipping. You see I'm skipping? Skipping. I haven't finished yet. Okay. Now, still haven't finished. Where am I skipping? Okay. Estimating survival functions. Now I want to get that. That's where I want to start. Okay. If I spent on this many slides, I'd never get to the rest of this. Okay. Now you might say, well, you'd never, if by skipping it, you're not understanding it. You're not going to understand anything. Well, I think I'm going to still try to make you understand this anyhow. Okay. Now estimating survival functions. Okay. Now. There are two things I'm going to describe. If it turns out nobody's censored, you have non-censored data, everybody failed. It's a very simple way to estimate the survivor function. What is a survivor function? It's giving you a probability of the number of people that are at risk at any given time. That's the denominator, and the numerator is the number of people that failed. So it's dividing the number surviving past time t. People who survive past time t, that's the probability, that's survival at time t. Number of people who survive past time t divided by the number of people that you started with. If there's nobody censored, you don't have to worry about anything else, about people not having the same amount of follow. Everybody's been followed for the same time until somebody fails. Okay, so it's the number surviving past time t divided by the number of people at risk at the start of the study. Now, if there's censored data, it's a little bit more complicated, and because you have to somehow deal with the fact that some people have dropped out of the study, and you can't get the formula in this simple way. And so there are two methods for dealing with censored data. One is called the Kaplan-Meier method, and the other is called the life table method. And we're going to only talk about the Kaplan-Meier method because that's the method that sort of generalizes to what the Cox model does, and that's the method that most people use, even though the life table method is another approach which uses grouped failure times, whereas the Kaplan-Meier method uses ungrouped. So I'm going to focus on the Kaplan-Meier method, as I said, because it is a special case of the method for computing adjusted survival curves for a Cox model. It's related more to the Cox model. Okay, so again, here's that data set we're looking at. At this point, I'm not looking at any other variable other than the exposure variable. And the exposure variable is treatment status. Are you in the treatment group or in the placebo group? Okay. So we're going to look at these two groups. Now, let's look at group 2, where this is where everybody failed. So let's say, how would we get the survivor curve for the data where everybody failed? Well, here's a picture of it. And here's a description of it. Okay. And here's a description of it, how it was done, and here's a picture of it, okay? And you notice it's a step function, right? That's what I've drawn here. It's not a curve. And the steps change at every time that somebody failed. And this is group 2. How many failures were there? Well, the number of failures, you see, these are the ordered failure times. How many failures were there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 failures. But that is, there were 21 failures, but there were 12 times at which somebody failed. There were 21 failures, but there were only 12 times at which somebody failed, because if you go back to the at time 1, 2 people failed. So that you're only going to count time 1, on this table. You can put that in once, because that's the earliest time that somebody failed. The second earliest time is 2, and so on. Okay. And now, in the second column is n sub j is the number in the risk set at the time, or just prior to the time that somebody failed. At the beginning of the study, all 21 people are in the risk set. And you notice nobody failed at the beginning of the study, and also nobody was censored at the beginning of the study. So the m sub j, or m sub 0, and q sub 0 is 0. And the survival probability is 1, because everybody in the risk set, everybody survived. So it's 21 over 21, that's 1. Okay. Now, at time 1, there were 21 people in the risk set also, because just prior to the time, that's the way you have to think about it, just prior to the time that somebody failed at time 1, or week 1, everybody was there, okay? And then what happened just at week 1, or between week 1 and the second time that somebody failed, which is week 2, 2 people failed. And no people were censored, okay? Because nobody was censored, everybody failed, okay? So the Q column is all zeros over here, okay? So what's the probability of surviving past time 1? Well, two people failed, so 19 people survived, 19 over 21. So that's the survival probability. I plotted up here, 19 over 21. That's here. That's the first time that somebody failed. And I plotted at time 1. Okay. What about time 2? Well, 2 more people failed. Okay. Now, but I don't have to worry about people who were censored here. So if I want to ask the question of the total number of people that I started off with, which was 21, how many survived of this 21 people up to this point, time 2, or just survived past time 2? Well, 2 people failed at time 1 and 2 people failed just at time 2. So 17 people survived. So it's 17 over 21. So I'm getting all these probabilities by considering the number of failures and dividing by 21. And I get these numbers, 0.90, 0.81, so on, and then I plot them. And then I plot them, and I keep dropping at different points at which somebody failed. And so it's not a smooth curve because I only have, what did I say, 12? I'm not sure. 12 different times at which people fail. It's not an infinite amount, so I'm only going to get a step function. And it's going down, which survival curves should do. So that's the survivor curve for non-censored data. And it is an example of something called the Kaplan-Meier curve, but it's, you don't have to worry about the issues you have to worry about with Kaplan-Meier. So it's a Kaplan-Meier curve, but it's simpler. Okay. In fact, if you look at this, if you look at, for example, if you look at, you see it says S hat of 4. What does that stand for? It says, what's the probability of surviving past 4 weeks? Okay, that's what this is saying. What's the probability of surviving past 4 weeks? Now, you notice, go back here, the probability of surviving past 4 weeks is 14 over 21, right? There it is, 14 over 21. I didn't have, you know. But it also turns out that you could have written it 1, which was the first one, times 19 over 21, times 17 over 19. So why is it 17 over 19? Why is it 17? Where's the 17 over 19 coming in? 17 over 19. Once you're at the second time that somebody fails, how many are in the risk set up to time 2, the second time that somebody fails? If 2 people fail, there's 19 now. How many of those 19 people survive? 17. So once you get to past the first one, then you have 19 left, and 17 of the 19 were still around. And then once you have 2 more, then there's 17 left. And 16 of the 17, if you keep looking at these, 16 of the 17. So I can actually get this number, the number for S, the 4th time at the, I'm looking at the wrong group here. Whoa, this group. Survival time at 4, which is 0.67, which is 14 over 21. I can also get that by 19 over 21, 17 over 19, 16 over 17. When you think about what happens, the 19s cancel out, the 17s cancel out, and there you go, 14 over 21. So it works by considering what happens at any time times what happens at the next time, given somebody got to that time, times what happens at the next time, given somebody got to that next time. That's what you're doing here. Probability of surviving past time 1, given that you've survived up to time 1, is 19 over 21. The probability of surviving greater than 3 weeks, given that you've survived up to 3 weeks, is 16 over 17. And if you put these in here and you multiply them together, you wind up getting what you don't need to have. You didn't need to multiply them together. You would get this number, 0.67. So so this formula is sometimes referred to as the Kaplan-Meier formula. Okay. So and it's called a product limit formula. Why is that? Well, first of all, where's the word? Why is it called a product limit? Why is the word product in there? Because you're multiplying. Okay. Why is it called a product limit formula? Where's the limit come in? Because it's not an infinite formula. It stops at some point. There's a limit to how many you can put in here. And in fact, you only have 1, 2, 3, 4, 5 terms in this formula. If you wanted to get the survival probability at 8 weeks, you have more terms in there. But it stops at some point. It stops when you're talking about 8 weeks. So there's a limit to how many terms you're going to put in the product. That's why it's called product limit, if you wanted to know that. Okay, so now we're talking about group 1. How do you do group 1? Okay. Group 1, you notice that at time 0, there were 21 people in that group. Nobody failed. Nobody was censored. At the first time that somebody failed was 6 weeks, and there are 21 people in the risk set at that point, just prior to that happening. 3 people failed, and 1 person was censored. Okay. So what I've done now is I said, well, at this point, I'm not even worried about the people who are censored. I said, what's the probability of survival terms? What's the probability of surviving past 6 weeks? Well, this person who was censored at 6+, Did they survive past 6 weeks? Yeah, they did. You don't know whether they failed at 7 weeks or 10 weeks. You don't know. You actually know they failed before 7 weeks, but you know they survived 6 weeks. So the probability of surviving past 6 weeks is 18 over 21 because 3 people failed and 18 survived. And this person isn't counted in there. So you got 0.8571. So that's the first dip in the formula. I guess I have the first dip in there, 8.8571. Now you got this next issue is, okay, the next thing you have is 3 people failed and 1 person was censored. So what happened was you have to deal with this censorship thing. So now at the next time at which somebody failed, you don't just have 18 people in the risk set, you have 17. Because not only did you lose these 3, you lost this one. Because this one wasn't there at time 7. So now you have 17. And 1 person failed and 1 person was censored. But you're not going to count this person there either. But at time 7, at week 7, it turns out, of the people that were at risk, and there were 17 of them, 16 of the 17 survived. So 16 over 17 is the probability of surviving past a certain time, given that you survived up to that time point, survived up to time 7. And then what you do is you multiply it by the previous thing you did, the previous thing you computed. So, so to get the survival probability at week 7, you take the survival time at week 6, and you multiply it by the probability of surviving past week 7, given that you survived up to week 7, and that's how you get the next one. And it goes on like this. So this is the formula for the Kaplan-Meier thing, which allows for censorship because it allows the risk set to change. And it still says, well, once you get to a certain point, once you consider what's at that point, you then consider the probability in the risk set that is available at that point to get the Kaplan-Meier curve. And so that's how you get all these different probabilities. And in fact, all of this comes from a simple formula. If you remember when you learned your first probability, you took your first course about probability. You remember there was a formula that said if you have 2 independent events, probability of A and B occurring at the same time was what? If they're independent, what is it? Probability of A times the probability of B. Okay. But if they're not necessarily independent, you got 2 events that are not independent, then the probability of A and B is the probability of A times the probability of B given A. That's something I think you may have also learned way back last year or when you were in elementary school. I'm not sure. You didn't learn that in elementary school. But anyhow, that's the formula that's being applied here. That's really the formula that's being used. And without, I talk about that in the textbook and all that, but what it comes down to, if you say, it's a little tricky here because if the event A is the failure time being greater than or equal to TJ, the time failure at time J, or ordered failure time at time J, and B is the failure time being greater than. So this is greater than or equal to, and this is greater than. What's A and B? What's the event that somebody has both A and B? Well, it has to be A is just a little bit more than B because it includes T of J. So A and B is just B. I don't know if you can see that. A and B is just B because if somebody is in both A and B, then their survival probability is greater than T of J, but not necessarily equal to T of J. And then you could actually, write down, well, P of A and B is the probability of B. That's the survival time greater than at time Tj. And then you could also write that the probability, with a little thinking about it, the probability of B given A is this probability of surviving past Tj, given that you survived up to Tj. And it turns out, it works out that that's the formula for it. Comes from this thing, so you may want to look at that and think about it some more. But it comes from the simple relationship of the probability. But there's a key thing. One key thing is that between the last time that somebody failed and the next time that somebody failed, there were no failures. And that's what makes this thing work. There are no failures during the time between the j minus first time that somebody failed and the jth time that somebody failed, because these are the next two times that somebody fails. And this makes this thing work. But I don't really want to do much more than that. And so in any case, you can take, what you've got for group 1 and what you've got for group 2, and you can plot them separately, or you can put them together. When you put them together, this is the picture you have for the two curves, okay? The two Kaplan-Meier curves. And when you look at these two curves, what do you want to do with this? What do you want to do with this? Well, one thing you want to do is you want to be able to say, well, which group is doing better as far as survival? And what do you see when you look at these two curves? Well, if one group has a survival curve that's above the other group all throughout it, then that group that's above it is doing better. Its survival probability is higher throughout the whole time of the study, right? So group 1 is doing, well, sort of. I mean, up here, until somebody fails, you can't start talking about that, but from here on in, group 1 is doing better, okay? Group 1 is doing better than group 2, okay? Now, is that all you want to do when you're comparing survival curves? Well, you don't want to simply say whether group 1, you also want to be able to say, well, is group 1 always better than group 2? Is group 1 always better to the same extent as group 2? When you compare group 1 and group 2, are they always like equally distant from one another? But what do you see from this picture? I mean, what could it's a rough conclusion, but what could you conclude from this, roughly? Well, that early on, group 1 is always better than group 2. But early on, it's a little bit better, and later on, it's a lot better. Isn't that what that says? That's what it says. Okay? So that's the type of thing you want to do when you look at survival curves. It could be that up to a certain point, group 1 and group 2 were no different from one another, and then later they separated. So that's the type of thing you want to do when you look at survival curves. You want to be able to compare them. That's one thing you want to do. You also want to be able to, well, this is the actual estimate of the survival curves. What else might you want to do? Remember we talked about 3 things you generally want to do when you got some kind of analysis you're doing? The hazard ratio, you want to get the point estimate of the hazard ratio. What else do you want to do? You want to test the hypothesis. What hypothesis would you want to test? Whether there's a significant difference between what? The two survival curves taken together. That's what you want to test. The null hypothesis is that there's no significant difference between the two survival curves, taking all the data together. And what's the name of that test? That test is called, I assume you prepared for this, not necessarily. The test is called the LogRank test, okay? The test that allows you to compare 2 or more survivor curves is called the LogRank test, okay? So that's one thing, another thing you want to do. And another thing you could also do is you can get confidence intervals around each curve and compare the confidence intervals. That's a little bit more trouble. I talk about that in the textbook, but we're not going to get into it here. But I am going to talk about the LogRank test, what that is, and how it works, okay? So here it is, the LogRank test for 2 groups, okay? Now, you're asking are the Kaplan-Meier curves statistically significant? In other words, I'm not controlling for any other variable. So I've got a Kaplan-Meier curve for the crude data for one group, and I've got a Kaplan-Meier, and I don't have adjusted Kaplan-Meier curves. I don't have adjusted survivor curves. To get adjusted survivor curves, I have to do something with a model. So I'm not doing adjusted survivor curves. So a statistically significant, the statistical equivalent, the null hypothesis is that they're no different, okay? Now, it turns out the LogRank test for 2 groups, actually the LogRank test allows you to do it for more than 2 groups. You can do a LogRank test for 4 groups, 4 different survivor curves. But right now we're talking about for 2 groups, okay? So for 2 groups, and it turns out it's also true for more groups, it's a chi-square test, okay? And it's a chi-square test where you have a computer program and it'll give you the chi-square statistics. So you don't want to actually compute it yourself. You want to have the program do it, okay? And it's a test that gives you an overall comparison of the 2 curves, an overall comparison. The way it works is it compares something about observed versus expected counts, considering how people failed or survived over the time of the follow-up. And the categories are defined by the ordered failure times. So that's sort of roughly what it is. It's a chi-square, you're going to get a chi-square statistic. Okay. Now, I could spend some time, I'm going to spend a little bit of time. Here's a table that describes how it works. Okay. Now, I don't want to spend the next half an hour talking about this table. Okay. But I just want to say a little bit. Now, first the thing I want to say is, in this table, you notice that, well, first of all, you see the number J, 1, 2, 3, 4, up to 17, but you notice that T of J is 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 23. Now, these values are all the times, the ordered failure times for both groups together. I mean, for example, if I go back to the original data here, where is it? Where is it? Okay. What's the largest failure time? What's the largest time at which somebody failed? Not the largest censored time, the largest failure time. 23, right? And there's somebody in each group that failed at 23, right? Somebody failed at 22 in each group. And then in group 2, somebody failed at 17, but nobody failed at 17 in group 1, but somebody failed at group 16. See that? So if I go back to this thing, where is it? Oh, I'm going the wrong way. That's stupid. Okay. See the 16? That's somebody in group 1, and that's somebody in group 2, the 17. So what I'm doing is I'm putting all the data together to figure out this LogRank test. Okay, and then what I do is you see the M, there are two M's, there's two columns here of M's. The first column is counting the number of failures in group 1, and the second column is counting the number of failures in group 2. Now you notice that in group 1, you see there's a 3 over here. What does that correspond to? The first time that somebody failed in group 1, which was week 6. Notice there's a 2 over here for group 2. That's corresponding to the 2 people that failed at the first time week 1 for group 2. So I'm putting in the number of the counts of failures for each group, but I'm doing it in separate columns. That's what I'm doing. And these are the observed failures. Okay, these are the observed failures for group 1. These are the observed failures for group 2. And now I also have, in the next 2 columns, I have the risk sets. Or that is the numbers in the risk set, the number of people in the risk set. And it changes because you notice in group 1, it's 21, 21, keep going to 21. It doesn't change until you go to the second time that somebody fails in group 1, because the first time was at time 6. But it changes immediately for group 2 because the 2 people failed at week 1. So this thing looks different. Okay, so, but anyhow, these are the observed counts, failure times, and then these are the expected failure times. And then you have to compare observed versus expected is what goes on here. Now, let me just show you. Let me just show you for one of them. Okay. Now, look where it says, see expected 21 divided by 40 times 2. And this is 19 divided by 40 times 2. Where's that come from? Where's the 21 by 40? Where does the 2 come from? It's the same 2. Where does the 2 come from? Well, 2 people at this time, 2 people in both groups, overall both, although it happened to be in one group, 2 people failed. 2 people failed. That's the total number of people that failed. Okay, now what I'm going to say is, how many of the 2 people who failed at this time would I expect to have failed? If there's no, say I'm doing a test of hypothesis, I'm saying if the 2 curves were equal, if there's really no difference between the 2 survivor curves, the only thing that would affect what the expected number would be would have to do with how many people are at risk in each of these things. So there's 21, now the total number of people that are at risk here are 21 plus 19, right? 21 in one group, 19 in the other, you add them up and what do you get? 40, okay? So I divide 21 by 40 here and 19 over 40 by here. Why 21 over 40? because that's the proportion of the total people at risk that were at risk in group 1. And this is the proportion of the total people at risk in group 2 is the proportion is 19 over 40. So I would expect to get 21, in other words, you notice this number is going to be larger than this number. I would expect to get more people failing in group 1 than in group 2. Why? Because there's more people at risk in group 1 than in group 2 at that time. That's how it works. Okay, for what it's worth, that's how it works. Okay, and then you wind up getting observed and expected, and you add up all the observed, and you wind up you get observed. For example, there's 21 people in 21 failures in group 2, 9 failures in group 1, and you get the expected and the in each of the groups, and then you take observed minus expected. Remember that whole thing when we did chi-squares way back, when you did that, observed minus expected, and that's somehow going to go in, and when you do observed minus expected and you have only 2 groups, it turns out the sum of the observed minus expected, even though these numbers are different, these numbers are the same. Well, actually, this is a negative, but it's still 10.2, so you're going to get the same number, other than one is going to be negative and the other is going to be positive. And that's what's used in terms of the test statistic. In fact, I'm just showing you how what the computer would be doing, but as far as you're concerned, the computer's going to do it, right? Showing you what the computer's doing. And then what you do is you compute this test. And again, you let the computer compute the test. And there's a formula for it, for the log-rank statistic. You see O2 minus E2? Well, O2 is the total number of observed in the second group. And E2 is the total number of expected in the second group. Okay, that's what O2 and E2 is. So go here, O2 minus E2, one is 21 and the other is 10.74. I subtract one from the other, I square it, and I divide it by something which is somehow, it's an estimate of the variance of the difference, which is a messy formula, and that's one reason why you want to let the computer do it. This is the messy formula, but this is what gets computed, and it's a chi-square with 1 degree of freedom. Now, the reason why it's a chi-square with 1 degree of freedom and not 3 degrees of freedom is because you're comparing 2 groups. You're comparing 2 survival curves. If you're comparing 3 survival curves, what do you think the degrees of freedom would be? 2, right? It's always 1 less the number of groups, survival curves you're comparing. Okay? So there is a formula for 3 groups. But anyhow, okay, so I computed and I get 10.26, which is that O minus E for the second group squared, and it turns out the variance is, whatever that thing is computed, is 6.2. I divide one by the other, it's 16.793. It's a chi-square statistic with 1 degree of freedom. Is that significant? What's the critical point, the cut point if you were doing a 5% test? P-value, your alpha was 0.05, and it's a chi-square. Anybody remember what that is? You should know. You know what it is if it was normal distribution. What's the cut point for a 5%? 1.96. What's the square of 1.96? 3.84. I mean, that's another number you ought to know, but some of you don't know it. You know, that's okay. You know 1.96. You do know that, right? You square it, you get 3.8. That's the cut point. Is this greater than 3.84? Yes, so this is highly significant, so there's a significant difference between the 2 curves, so we just did the log-rank test. Okay, now, how do you do this? Well, there's a couple of shortcut formulas, but where you can actually go, remember you might have learned O minus E squared over E? Well, that's sort of another way to do it, but you don't need to do it because it's not as good as the log-rank test formula. So even though I have this approximate formula, who cares? I should have gotten rid of this. I'm just showing you that there is something, but we don't care. Okay, now, if you're talking about more than 2 groups, if you're allowing the number of groups to be 2 or more, then the log-rank statistic has it's a chi-square, but it has G minus 1 degrees of freedom, where G is the number of groups. 3 groups, meaning it's a 2 degree of freedom test. 5 groups, it's a 4 degree of freedom. And the null hypothesis is that all survivor curves are the same. That's the null hypothesis. If you reject it, you say somehow there's a difference between the 5 survivor curves you're comparing. It doesn't say where the difference is. So then you might want to, you may have learned something in the course with Bob Lyles, and if you find that there's a difference in 5 curves, you may want to look at pairwise differences. Did you learn anything about that? Not sure. You might want to do that. See whether, well, is this the pair different? Is that pair different? But basically, that's what you do. Now, the formula, when there's more than 2 groups, is a real mess in the sense that it's not even easy to write it, and there's a matrix way of doing it, which is matrices is something that you're not going to worry about in this course very much. You saw a matrix, though. Did you see a matrix in this course? Have you seen any kind of a matrix? Well, you saw the correlation matrix. What's a correlation matrix? It's an array of correlations. So that's a matrix. It's an array of numbers. So but it's a matrix. Who cares? Okay. But anyhow, it turns out that the program that you want to, this is what I want to get to. The program that you want to use is called life test. Program. This is how you do it. So this is the most crucial thing I could say about everything I've said so far. How do you do it? Okay. Now, the name of the data set it's a remission time data set. I gave it a name. I called it Anderson because that's where the original data set came from. And it turns out the data set that I described to you up to this point, there was survival time, there was a variable called status, whether somebody failed or was censored. You had treatment status, you had log white blood cell count status, and there's another variable that I've now added to the data set that came from this study, sex, whether you're male or female. So there's now 3 variables that you're considering. The main question of interest is what? Is there a significant difference between the 2 treatment groups? And you may want to control for these other variables. Okay, now if one of the variables, log white blood cell, as we know, is continuous. So if we wanted to do a log rank test to compare different categories of the log white blood cell count, that's not the main variable of interest. But if we wanted to see if survival curves for different log white blood cell counts are different, we'd have to categorize log white blood cell. You can't just do it treating it continuously. So what I did in these statements over here, the next 3 statements, is I put log white blood cell count into 3 categories. Less than or equal 2.3, between 2.3 and 3, and greater than 3. So if I want to do a log rank test and I have a continuous variable, I have to categorize it, and then I get 3 survival curves. In this case, I did it in 3 groups. I'm going to get 3 survival curves. I'm going to use this log rank test procedure. Now, look at what's down here. Proc life test. The name of the program is life test. That's the name of the procedure. Data Anderson. That's the name of the data set. Method KM, well, Kaplan-Meier, right? Plots, see S and LLS? What does S stand for? Survival curve, okay? Right? What does LLS stand for? You don't know. You're not sure unless you go on and read on. We're going to eventually talk. LLS stands for something called the log-log survival curve that we're going to explain a couple of classes down the road. You can plot either just the survival curve by itself and not put in LLS, not plot this log-log, but eventually you want to do that. You can get both these plots, okay? Now you see where it says time. So if you just put an S, and you said S, close the parentheses, that's all you need to do to want to get the Kaplan-Meier plots. Time, serve T, star status 0. What's being done here? What are you doing in that statement? You're telling the program, which is proc life test, what the time variable is, right? And you're telling the program what's this other variable? Status. What's that variable? That's whether somebody failed or was censored, right? That's the other variable. You have to tell both those things, because if you just tell survival time, you have to know whether somebody failed or was censored. So you have to tell them both. And the way you do it is you put a serve T star. It doesn't really mean you're multiplying it. You're just telling the computer that I need to have these 2 things. That's the way you write it. And then it says, you see it says parentheses 0. What's that? Well, that's the value that you're giving in your data set for somebody who's censored. For somebody who fails, the value you gave is 1. For somebody who's censored, you give the value 0. Then you could have another value. You could have 8 for somebody who's censored. If that was the case, you'd put in 8 over here. But if you're defining somebody who's censored, giving them the value 0, then that's what you put in here. It's the value of the variable that describes whether or not you're censored. And then it says strata Rx. And then it says strata LWBC. And then it says strata set. So what's going on here? What's doing? What's happening? What are we doing? I'm getting a log-rank test. Or not only that, I'm getting Kaplan-Meier curves, but I'm also going to get a log-rank test if I do these three statements. For what am I comparing? What's this one doing? What's this one doing? The two treatment groups. What's this one doing? Well, I've defined this new variable LWBC, which has 3 categories. And so basically what I'm doing is I'm getting these 3 strata, these 3 survivor curves for these 3 categories. I'm going to do a log-rank test and a Kaplan-Meier curve for those 3. And this says sex, so I'm going to do for males and females. And I run this thing, I'm going to get an output. So let's look at the output. Boom. Here's the output. Okay. This is comparing the 2 treatments. Does this look familiar? Well, this is a picture of what I already showed you when I talked about the Kaplan-Meier curves. This is what the computer prints out. But this is, you remember how the treatment, the difference in the groups wasn't that it was closer early on and further later on? These are the 2 Kaplan-Meier curves. The computer automatically did it. You didn't have to do it. Okay? So there you get that for the treatment group. Okay? Now, in order to do this, placebo was labeled as 1 and treatment was labeled as 0. Why did I do that? Why was that done in the data set? I didn't show you the data set exactly, but why was that done? You remember when I talked about, you remember when we got the hazard ratio was 4.6? And in order to get a 4.6, I had to divide the placebo hazard by the treatment hazard in order to get a number larger than 1? Well, in order to do that, I have to define the placebo with a 1 and a treatment with a 0. Otherwise, I'm going to get a hazard ratio. I'm going to get some kind of comparison. It could be less than 1. Okay, so that's why it's 1 and 0. But anyhow, regardless of that, it wouldn't have mattered either way. I would get the same 2 picture. But look down here, test of equality over strata. You see this log rank statistic? See where it says log rank? See that number 16.7929? Well, did we see that before? There it is. 16.793 down here, right? There it is. That's the log rank test. And that number comes right directly from running life test, running the procedural life test. It's chi-square and it's significant. So there's a significant difference between these 2 curves. Now, there are other ways to do tests, compare groups. There are other tests. Another one is called the Wilcoxon test. Okay. Now, you notice the Wilcoxon test, the value is less. See, the number is less. It's not as significant, even though it is significant, right? Now, it turns out that this test called the Wilcoxon test, and there's a sort of a parallel test, which is almost the same thing, not exactly, called the Peto test. But this test emphasizes, in doing the chi-square, emphasizes the earlier part of the curve in making the comparison. The earlier part of the 2 curves. Now, if you look at the earlier part of these curves that you're comparing, is there a bigger difference earlier or a bigger difference later? Bigger difference later. So if you wanted to compare what was going on and emphasize what's going on earlier, would you expect to get a higher chi-square or a lower chi-square if you're emphasizing earlier? Lower, and that's what you got. Okay? So the Wilcoxon test, if you decide you want to emphasize the earlier part of the curve, now when would you want to do that? When would you want to do that? Emphasize the earlier part of the curve. Well, there's a lot of reasons why people want to do things. It could be you're only interested in what's happening early on. You're not interested in, letting the study drag out, or you think people are failing early on and you want to look at what's happening early on. So it could be, that's one thing. It could be previous studies showed something that early on there was a big difference, or you want to emphasize early on. If you don't want to emphasize early on, you do the log-rank test. You want to emphasize early on. There's ways you can actually emphasize later on compared to early on. All that stuff. I mean, you can imagine statisticians try to figure out different ways to do things, to consider every possible choice you can have. But, okay, that's okay. Now, look at this one. These are the Kaplan-Meier curves for the 3 log white blood cell variables, 3 categories, log white. What about that? Well, see, the log-rank test is 26, and you see it's 2 degrees of freedom? Why? 3 curves. Big deal, right? This is easy, right? Now you notice it's 20 with 2 degrees of freedom for the Wilcoxon. Can you sort of figure out why? Well, again, early on, and then this is not looking at the treatment variable, it's looking at a variable you want to consider for control. But if you look early on, they're not as different as they are later on, even for this variable, right? So you might expect the Wilcoxon test to be less, as it is. Okay? You agree? Okay? Okay, now what about this one? This is the sex variable. What happens here? What's a little strange here? These are the Kaplan-Meier curves for the 2 groups, males and females. Well, early on, females are doing better than males. And later on, males are doing better than females, right? Isn't that what it says? Right? Do you want to really do a test for this? It looks like you get a different comparison. You want to do an overall test to compare these 2 curves. If it turns out it depends upon whether you're early or later. In fact, when you think it depends upon whether you're early or later, what does that sound like? The effect depends upon, doesn't it sound like interaction? The effect of interest, comparing the, in this case, the effect of males versus females. In this case, that's what you're comparing. It depends upon whether you're talking about early in the study or later in the study. So you might not want to do a log-rank test if it turns out you get a picture like this. In fact, you notice that the log-rank test gives you a chi-square of 0.5569 with 1 degree of freedom. Significant? Strongly non-significant. Okay? Would you then conclude that the males and the females are they're both estimating the same thing? It looks like there's a very different thing going on. Depends on whether you're early or later. One does better than the other, early versus later. So you may not want to do the log-rank test if you're talking about if you're talking about you have interaction over time. Okay. Now there's something that you say, well, what do you do if you have interaction over time? We'll talk about how to do that later. Okay. Anyhow, you can do this in Stata and so on. So I've done this in Stata. And I want to show you a second example before I sort of quit today, almost before I quit. Here's a different data set. This is not the remission time data set, a different data set. I want to illustrate a point. This is this is called the veterans data set. I actually showed you a little bit about this, or gave you an example when I was talking about collinearity, because I was showing you an example where the collinearity, maybe I did, maybe I didn't, I'm not sure. But anyhow, the outcome variable is time until somebody died. These are all people who have cancer. They have lung cancer, okay? And you're comparing 2 treatments, standard versus a test treatment, okay? And the subjects in the study have different kinds of cancers. They either emphasize large, adeno, small, or squamous. There's 4 different types of cancers that they could have, or tumors that they can have, I should say. Okay, and this is a variable with 4 categories. If you wanted to actually fit a model with the 4 categories, what would you have to do? 3 dummy variables for the 4 categories. But we're not really at this point doing. What we want to do is we want to compare. Treatment groups, you want to compare the cell type. If we wanted to compare the 4 cell type groups, how many survival curves would we have? 4, right? 1 for each one, okay? So, and then there's some other variables, performance status, disease duration. Now, I want to show you something. Here's what happens when I look at, well, actually, this is not the cell type variable. This is the performance status variable. These are people with, again, lung cancer, and the question is, how well can they carry out everyday activities? Quality of life type of thing? That's what you're sort of asking. It's a continuous variable, okay? But in order to do a log rank test for any continuous variable, you have to stratify, you have to categorize it. So what I did was, I considered 3 categories of this variable, performance status. High, medium, low, and there were 50 in this group, 47 in this group, and 31 in this. So I'm getting 3 survivor curves. And that means I'm getting 3 survivor curves, and the log rank test is going to have 2 degrees of freedom, right? Now look at these 3 survivor curves. Look at these 3 survivor curves. And I got the output here, over here. Now look at the 3 survivor curves. Early on, are these survivor curves closer or further apart than they are later on? Look at this. Just want to give you an example. Are they closer together early on, or are they further away later on? Early on. What am I saying? Early on, are they closer together? No, they're further apart early on, right? You can see this, right? They're more spread out. Later on, they're not that far apart compared to what they are early on. So if you're going to do the log rank test, it's not going to emphasize early versus later. If you were going to do the Wilcoxon test, what would you expect to happen? Would you expect the chi-square here to be larger or smaller than the chi-square? You know, would you expect the chi-square to be smaller than the, I mean larger or smaller than the log rank test? Now look at the log rank test. Log rank test is 29.8. The Wilcoxon test is 47.16. Which is larger? Wilcoxon. Why is it larger? Because early on they're more apart, right? And so that's what it's doing. So the log rank test doesn't sort of distinguish between early versus later. And the Wilcoxon test does. And there's a variation on that called the pedo-pedo test, which is almost the same answer, not exactly the same. It's numerically a little bit different, okay? And then there's even something called, I mean, this is where statisticians like to try a lot of things. There's the Flemington-Harrington test, okay? This was trying to give more emphasis to the later part of the curve than the earlier part of the curve. You see 1, 3? The earlier to the later is more emphasis to the later part of the curve. You notice the chi-square is 0.33? You're giving more emphasis to the later part. You can do these other, but usually the question is, do you want to emphasize the earlier part or the whole thing? How are you going to make that decision? Earlier or the whole thing? Well, it depends. It depends upon what you're studying, what you think about, what makes sense in terms of the literature and all that. That's what it depends upon. Okay. You can always compute the two, and if you computed the two, well, in each case it's significant, it doesn't matter. If one was significant and one wasn't significant, it might matter. Okay. So anyhow, that's that. Now, only other thing to say is that the Wilcoxon and the log rank, the Wilcoxon test emphasizes earlier, the Wilcoxon and the pedo that represent earlier part of the curve. Now it turns out, you remember I showed you this formula O minus E in the formula for the log rank test? It turns out that's replaced by N times observed minus expected. N is the number of people in the risk set. Now let me just say one thing. N is the number, if you're doing a survival study, how many people in the risk set, what happens with the risk set? It starts large and it gets smaller, right? So early on, the number in the risk set is larger than it is later on. So if you're going to compute a test statistic where you're going to emphasize the number in the risk set and the difference between observed minus expected, then what you're doing is you're giving more weight to the earlier part of the curve. That's what this is. That's what this does, sort of, for what it's worth. It doesn't matter. You don't have to worry about this, the mathematics of it. You just have to use the computer program to do it and then interpret it. So I think that's almost it. Yeah, that's really it. Okay. Comparison, we've just done that, and the matrix formula. So we're done. Now there's a couple of other things in this thing where I talk about the hazard function, but we're done. It's 20 after 5. Let's have a weekend. Is this Halloween? No. Is that next weekend, right? You know, one of our faculty, do you know Michael Kramer? How many know Michael Kramer? Well, if you're in any of his classes, what Michael does, he invites his class or his students to come over to his house over the weekend to carve pumpkins. Okay? I don't do that. I just wear shirts. Okay.
I found this in the restroom. I don't know who it is, but it's a modeling binder. I don't know if you want to announce it before everyone.
There's a modeling binder. Somebody left a modeling binder. EPI 740 in the restroom.
No. Okay.
Okay. I'll take it. Thanks.